The next stage of this investigation is not about making the discovery sound more extraordinary. It is about finding out whether the unusual observation survives serious scientific testing. When astronomers encounter an unexpected signal, they cannot immediately assume that it represents something new. The same data must be examined repeatedly, often by independent researchers using different software, calibration methods, and assumptions. That process is crucial. An apparent anomaly can sometimes come from an instrument, background radiation, data processing techniques, or an incomplete understanding of a complicated astrophysical environment. If the strange pattern disappears when the data is processed differently, the mystery may have a very ordinary explanation. But if independent teams continue finding the same effect, the scientific interest becomes much greater. That still would not prove the existence of extra dimensions, extraterrestrial technology, or a new form of physics. It would simply mean that something unusual has been detected. And that is where science becomes exciting. Astronomers have used gravitational lensing for decades to investigate some of the most massive structures in the universe. When enormous amounts of matter distort spacetime, light traveling from distant galaxies can be bent along its journey toward Earth. The resulting arcs and distorted images can reveal information about matter that cannot be observed directly. This includes dark matter, whose presence is inferred largely through its gravitational influence. If an observation does not match predictions, researchers first look for conventional explanations. Perhaps the mass distribution of a galaxy cluster was modeled incorrectly. Perhaps several objects overlap along our line of sight. Perhaps the instruments introduced a subtle systematic effect. Or perhaps our understanding of the environment is incomplete. Only after these possibilities have been carefully tested does a more fundamental explanation become worth considering. That distinction matters because one strange observation cannot overturn established physics. General relativity, for example, has survived an enormous number of tests. But successful theories can still have limits. Newtonian physics works remarkably well in many everyday situations, yet Einstein showed that a deeper description was necessary under extreme conditions. A similar development could happen again. Perhaps our current understanding of gravity is extremely accurate within the situations we have tested, while something deeper remains hidden at scales or energies we have barely explored. This is why the idea of additional dimensions continues to appear in theoretical physics. It is not because astronomers have photographed another dimension. They have not. Instead, some mathematical models allow for dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. But how could something like that appear from our perspective? Imagine a creature living entirely on a flat surface. It could move left, right, forward, and backward, but it would have no concept of movement above or below its world. If a 3-dimensional object passed through that surface, the creature might observe strange changes. A sphere could appear as a tiny circle, grow larger, shrink again, and eventually disappear. From the 2-dimensional perspective, the event might look impossible. From the 3-dimensional perspective, it would be completely ordinary. This analogy does not demonstrate that higher dimensions exist. It simply illustrates an important idea. Observations can sometimes reveal only a limited projection of a more complicated reality. That is why researchers must remain cautious. If a strange signal eventually disappears under better analysis, that is still a successful scientific result. If it survives every test, however, the question becomes much harder. Could our current description of gravity be incomplete? Could an unknown physical process be affecting the observations? Or could there be something about spacetime itself that we have not yet understood? For now, there is no confirmed evidence that Webb has discovered an extra dimension. The mystery remains a question, not a conclusion. And that distinction may be the most important part of the entire investigation. There is another extraordinary question that continues to capture the imagination of astronomers. Could an observatory such as the James Webb Space Telescope eventually identify convincing evidence of life beyond Earth? One nearby world often enters this conversation. Proxima Centauri b orbits Proxima Centauri, the closest star to the Sun at roughly 4.2 light-years away. The planet is especially interesting because it lies within the star's habitable zone, the region where conditions could potentially allow liquid water under suitable atmospheric conditions. But being in the habitable zone does not mean that life has been discovered. That distinction is essential. Proxima Centauri is an active red dwarf, and its powerful stellar activity could create a difficult environment for a nearby planet. Scientists therefore need to determine whether the planet has an atmosphere and, if it does, what that atmosphere contains. This is where spectroscopy becomes extremely powerful. When light interacts with molecules, specific wavelengths can be absorbed or emitted. By carefully studying those patterns, astronomers can infer the presence of particular gases. Water vapor, carbon dioxide, methane, and other molecules can potentially leave recognizable signatures. But even detecting one of these gases would not automatically prove life exists. Nature can create many of the same molecules through geological and chemical processes. The real goal is to search for combinations that are difficult to explain through non-biological mechanisms. That is one of the biggest challenges in the search for extraterrestrial life. Scientists must distinguish between a genuine biosignature and a false positive. A volcanic process, for example, could produce gases that might initially look interesting. Photochemical reactions driven by starlight can also create unexpected atmospheric compounds. This means that a possible signal must be tested against many different explanations. The same caution applies to claims about artificial lights. A distant planet producing unusual infrared emission would be fascinating, but it would not automatically mean that an alien civilization built cities. Thermal radiation, reflected starlight, atmospheric effects, surface minerals, and observational limitations could potentially create unexpected signatures. At the distance of Proxima Centauri, separating a faint planetary signal from the overwhelming brightness of the host star is an enormous challenge. This is why scientists rely on repeated observations and multiple instruments. If a strange signal appears once, researchers remain cautious. If it appears again under different observing conditions, interest increases. If independent observatories detect the same phenomenon and natural explanations become increasingly difficult to sustain, then the scientific significance could become enormous. But even then, the conclusion would need to follow the evidence. The most exciting discovery might not be a photograph of an alien city. It could be something much more subtle. A chemical combination in an atmosphere. A repeating signal whose origin remains unexplained. A planetary environment unlike anything found in our solar system. Or evidence that forces scientists to rethink how planets and atmospheres evolve around other stars. That is the real power of modern astronomy. The goal is not to confirm what we hope is true. The goal is to discover what is actually there. James Webb has given scientists an extraordinary new ability to study distant worlds, ancient galaxies, and faint cosmic signals. But every observation raises another question. And perhaps that is the most fascinating possibility of all. The universe may not be hiding one spectacular secret waiting to be revealed. It may contain countless mysteries, each requiring years of observation, testing, and debate. Some will eventually have ordinary explanations. Others may transform our understanding of nature. And somewhere in that enormous darkness, there may be discoveries that completely change the way humanity sees its place in the cosmos.